Well, we do join one. We are alive. We are alive. right, you're welcome to the section. Okay, so and in this section we are going to be considering did I write mass 203 here? This is not 203, this is 201. We are still in 201. Okay, and and then in this particular section we are going into module 3. Anywhere you can see that the exercises we are given are quite long, all right, and it's taking us a lot of time to exhaust, so but we will continue trying. All right, so from module 3 I'm beginning with question 1. Okay, so first of all let's run through this module. Okay, the module has about, let's look at it, it's page 18. Okay, page 18. It has about question 1, question 2, 3, 4, 5, then after 5, okay, yeah, the module has 5 questions. So before we get to module 4, which I think is the last module if I am correct. Okay, there's module 5. Okay, so it looks like module 5 is the last module, so we are still in module 3. Wow, we are still a distance away. All right, so let's begin so that we can run. So we have about 5 questions to go through in this module, down to page 28 from 18. Okay, so the first question here says that a vector. Now this is question 1a. Okay, so it's important that you note that. All right. So it says that a vector W is called a linear combination of the vectors v1, v2 to vp if what happens. Okay, so my name is do I need to tell you? You should know. Okay, so but meanwhile, if you have not subscribed to my channel, kindly do so. All right, of course you should do that to support the channel for the value that you get from it. It's very important. Thank you. Okay, so we said that a vector W is called a linear combination of vectors this if your W is equal to C1 V1 plus C2 V2 plus ... up to CP VP for some, okay, so for some scalars, C1, C2 up to CP. Okay, so sometimes we make use of Cn, that's if our V stopped at N. All right, so we are using up to CP now because our V stopped at P. So depending on what you have, you are going to be able to give your definition. All right, so this is a definition for linear combination of, for a particular vector to be a linear combination of another set of vectors. All right, and that's what they are asking for. Okay, so and that is just all for question 1a, and so we go over to 1b. So from 1b I'm going to be reading the questions because we may not have all the time to write it. Okay, so it says complete the definition. This is also another definition. All right, it says let V be a vector space and S equal to, okay, V is a vector space. Okay, I'll just be writing out some important information. V is a vector space and S, which is given as the set of V1, V2 up to Vn. Okay, so here we are using Vn, be a set of vectors. Okay, so this one now is a set of vectors. All right, so the question says a set of vectors in V, which is the vector space. So it says the set is called a basis for V if the following two conditions hold. Okay, so in other words, what they are asking us here is to state the two conditions for a set of vectors which are under a vector space to form a linear, to form where is it, to form a basis, to form a basis for that vector space. And of course, by definition, which we have already seen, there are two conditions, and that is what they are asking us here. So the first is that S, which contains these vectors, must be linearly independent. So our S must be linearly independent, must be a linearly independent set. Let's put it that way. That means all the vectors in S must be linearly independent. Okay, must be a linearly independent set. So that's the first condition that must be met. And then the second condition is that that particular S must span your V. S must span V. Okay, so these are the two conditions for your S to be a basis for a vector space. And meanwhile, basis is just that this particular set S has the capacity to produce the whole of the vector space by some linear combinations. All right, so that's what it means to span. Okay, so for instance, if I give you something like the standard identity, or the standard unit vectors, for instance, E1 equal to maybe 1 0 and E2 equal to 0 1. These are the standard unit vectors in vectors of R2, that's vectors of basis 2. Okay, so now these two vectors here, now if you put them in a set S equal to E1 E2, they have the capacity to be what do you call it now, to be a basis for R2, because they can generate the whole of R2 by some linear combination of this E1 and E2. So that's what we mean by basis. And so the conditions are that this set must be linearly independent, and then and we know what linearly independent means. Okay, so that they can only combine to produce 0 if their combinations or the scalars you're using to multiply are only zeros. Okay, so if that does not happen, then you say they are linearly dependent. Okay, and so to span now is what I was explaining. So it has capacity to generate all elements of V, by some linear combinations. Okay, so and that is that for C. Okay, so we go over to, for B, so we go over to question C. And so for C, we are told that is also another definition we are to complete. So, and I will read. It says that P is given as if P is equal to V1, V2, up to Vn. And so is a set of vectors in a vector space. Okay, V, so that means V is a vector space. Okay, and then we are told that then the subspace W of V, and so W is a subspace of V, consisting of all linear combinations of vectors P, is called dash. Okay, so all right, so what this is saying is that if you have a set of vectors P equal to this, all right, and is containing vectors in a vector space V. So that a subspace of V called W, is defined as dash. That's actually what they're asking us to do. So a subspace W, you can define as simply, a space that is spanned by this particular set of vectors. Okay, so we can say that subspace is that W, that in filling that space, you can see they said that this particular subspace of V consisting of all linear combinations of vectors P is called, okay, so is called dash. So okay, so in filling that, you would let us know that sorry, that it is the space spanned by V, that's spanned by P. Okay, so this W is the space, is called the space spanned by this particular P, or you can just say spanned by V1, V2 up to Vn, but you can just simply say spanned by P. Okay, so in other words, since W is a subspace of V and your P is a set of vectors under Vn, right, and then W is now defined as consisting of all linear combinations of P. Okay, so do you get that? Remember I said earlier on that a span is a set that has the capacity to produce all the elements of V by some linear combinations. Okay, so now if this question is saying that W consists of all the linear combinations of P, that means P spans your W, alright? So that's actually what they are trying to let you know here. Okay, so your W is a space that is spanned by P. Okay, so let's move on right now, and that is for for question C. Okay, so we go to D. So D says a subspace W of a vector space V must satisfy the following two conditions. Okay, so that's saying what are the two conditions for a particular subset of vectors or set of vectors that is a subset of a vector space. What are the two conditions for that subset to qualify as a subspace of the vector space? Okay, so one is that it should be closed under addition of vectors, and then it should be closed under scalar multiplication. Okay, so invariably what he's saying is that for all vectors, let me put it this way, so for all vectors u, v inside our W, okay, for all vectors u, v in W, your u plus v must also be in W. That's closure under vector addition. I've mentioned that. And then number two is that it must also be closed under vector multiplication. Okay, so for that we can say for all vectors u, I'm omitting that all, so or for any, you can just say for all or for any. So for all u in W, then your ku must also be in W, where k is a scalar, where our k is a scalar. That means an element of a field. Okay, so that's when we get to abstract algebra, right? So your k is a scalar, right? So once your a subset of a vector space is able to satisfy these two conditions, closure under vector addition and closure under vector or under scalar multiplication of vectors, then you say that such subset is a subspace of the particular vector space. Okay, and that's for question D. So we move over to E. So E is a so we have begun solving now. So all the while we have been defining. Okay, so look at this. So E is saying express minus 9 minus 7x minus 15x squared as a linear combination of P1, P2, P3, where our P1, P2, P3 are given as follows. Okay, so let me write them. So where P1 is equal to 2 plus x plus 4x squared, and P2 is equal to 1 minus x plus 3x squared. Okay, and then P3 is equal to 3 plus 2x plus 5x squared. Okay, so if we have P1, P2, and P3 as what we are given here, so the question is saying, can we express the following three vectors as a linear combination? Can we express this other vector given as a linear combination of these three? That means, is there any way we can pick up some scalars to multiply these three vectors to generate only this single one? Okay, and it's a very beautiful problem. And so let's see. Now the question or the exercise started with some hints in the solution. So ordinarily that hint should be obvious from the first definition we gave. For this to be a linear combination of this, what it means is that there exists some C1, C2, and C3, since there are three vectors, such that if you use them to multiply these three vectors, that means C1 P1 plus C2 P2 plus C3 P3, you are going to get these vectors, which is minus 9 minus 7x minus 15x squared. Okay, so that's the meaning of this vector forming a linear combination of these three. Okay, and that's the first thing they gave us in the definition. And then they said, of course, if you try to from here break down what you have here, you are going to form a set of equations. And so they did that and then formed only one and asked us to produce the other two, and then to solve for C1, C2, and C3, that we do what we just said. Okay, so let's now try. And how do you get those three equations? Just substitute the value of P1, P2, P3 here. So that means this is going to be C1 will multiply the whole of P1. So C1 times 2 is 2C1. Let me do it that way because of our time. So we have 2C1 and then C1x. Okay, so we are going to have plus of course C1 will multiply x to give you C1x, plus C1 will multiply 4x squared to give you 4C1x squared. Yeah, then we are done with C1, P1. We go over to this. C2 will multiply the whole of P2. So C2 times 1 will give us C2. And C2 times minus x will give us minus C2x. And C2 times 3x squared will give us plus 3C2x squared. And finally, this is going to be C3 multiplying the whole of this, which will give us 3C3. And then C3 will multiply this to give us 2C3x. And C3 will multiply to give us 5C 3x squared. Okay, maybe I should reduce this. Okay, all right, and then that is equal to, I hope you are still able to see this. Yes, and that is going to be equal to your right hand side, which is minus 9 minus 7x minus 15x squared. Okay, and so what did we do? We now try to collect like terms, so all the constants should come together. So you have c1 2c1, then this is another constant, plus c2, then this is another constant, plus 3c3. So all of these should be equal to the constant on the right side. We are now comparing polynomials, all right, and that's equal to 9 minus 9. So that's how the first equation was gotten. And if you check what we have in our hint on the material, you see that it's exactly this. And they are asking us now to get the remaining 2. So what do? Just pick the coefficients of x on the left hand side, and it should be equal to the coefficients of x on the right. And that's going to be, here you have c1 plus here you have minus c2, and then in the third one you have 2c3. Okay, that should be equal to the coefficient of x on the right hand side, which is minus 7, and that's equation 2. Okay, so finally, to get your equation 3, you will now pick all the coefficients of x squared, and so this is going to be 4c1, and this is going to be 3c2. Okay, and finally you have 5c3. Okay, and everything should be equal to the coefficient of x squared here, which is minus 15. And so this is the third equation. Okay, so and that these two now completes the first part of question we are asked, which is to find the remaining 2 equations. Okay, so now the other question we are asked is that we should now use the 3 equations we have gotten to now solve for the values of C1, C2, C3. And how do you do that? Just generate from here what we call the augmented matrix. So what am I going to do? I'm going to bring out all those coefficients 2, 1, and 3. And then on the other side, the augmented part, I will have minus 9. And then here I will have 1, minus 1, and 2. And then here I will have minus 7. This one will be 4, 3, and 5. And here I will have minus 15. Okay, so this is what I'm going to reduce now to be able to get the value of my C1, C2, C3. So what do? Remember that you can actually interchange these rows. Okay, in fact, let's do it that way. Let's interchange the rows. So if we do that, okay, so if we try to interchange the rows, we are going to have, let row 1 become row 2, and so on. So why are we interchanging the rows? Because the coefficient of 1, so we want the leading or the pivot to be 1, so that it will be easy to form our algorithm. And so still bring in your, what do you call it here, still bring in your minus 9 here. Okay, so here you will now have 2, 1, 3, and then, sorry, this is not minus 9, this is minus 7. Okay, all right, so this is minus 7, this is where we have minus 9, and so this one will be 4, 3, 5, and minus 15. Okay, so we are now going to be reducing this, and that's going to give us so to reduce this, we are going to have something of this nature. So we can say, let our new R2 be equal to, just have R2 minus 2 times this is going to give us 0. So if you say 2 times row 1 and then you're subtracting it from R2, you are going to get 0. That's actually what we want. We want to eliminate this, and then here we are going to replace R3 with R3 minus 4 times R1. Remember, you are using your this one as the pivot. All right, so that's what we are going to be doing. Okay, so in that case, your equation row 1 remains unchanged. So we just have 1 minus 1 and then minus 7. Permit me to shift this a little bit. Okay, so here we are going to have, okay, the next one, this minus 2 of this is 0. This minus 2 of this is going to be 1 plus 2, which is 3. This minus 2 of this is going to be minus 1. This minus 2 of this, that's minus 9 minus 2 of minus 7 will be plus 14, and that's going to be 5. And then we are over here, this minus 4 of this will be 0, and then this minus 4 of this, that's 3 minus 4 times minus 1, which is plus 4. This will give us 7, and this minus 4 of this is going to be 5 minus 4 times 2, which is 8, and that will give us minus 3. And then minus 15 minus 4 times minus 7 is going to be minus 15 plus 28, and that's equal to plus 13. Okay, so we have gotten the reduction from this one, this particular matrix, to another one. Okay, so we will now try to reduce that further. So what are we going to do again? We now need to reduce this 7 into 0 because we want to obtain a, an echelon form. Okay, so and how do we do that? We are also going to get another algorithm to reduce that, and it's going to just be only 1. So in that, we are going to be replacing only R3. And how do we do it? Just change, since there is no 1 here, assuming there is any 1, we would have interchanged again. Or if we could divide through, if you divide through by 3, now these 2 will become fractions, so no need, just leave it that way. So just interchange the numbers here as coefficients. So I'm going to have 3 times R3, okay, that's, I'm using this coefficient to multiply R3, minus 7 times R2, okay. So if I do this, I'm going to eliminate this to be 0 because 3 times 7 is 21 and 7 times 3 is 21. If you subtract, you're going to get 0. And so I'm going to apply that algorithm on R3. I'm going to use it to replace R3. So that means my R1 will be the same. I will have minus 1 here. R2 will be the same. I'll have 3 minus 1, 5. So R3 is what we are replacing. Okay, so let's go. So already this is 0. Remember, you are using R3, 3 now as your pivot. So this one will be 0. And then here, if I do what we said here, we'll get 0 here. Now let's do for the other 2. 3 times minus 3 minus 7 times minus 1. What's that going to be? That will be minus 9 plus 7, which is equal to minus 2. Okay, and then lastly, we are going to have 3 times 13 minus 7 times 5. What's that going to give us? This is 39 minus 35, and that is equal to 4. Wow, this is beautiful. Okay, so we have gotten our final reduction. I can remove this. So when you've gotten your final reduction, what do? You now break it back into your system of equation. And what is it going to be? Remember that this is still your constant side. So that means the whole of this will multiply your C1, C2, C3 again. It is going to be of this nature again. So you just attach C1, C2, C3 here. So you're going to have C1 minus C2 plus 2C3 is equal to the constant, which is minus 1. then the next one, this will be 0, so you start only from C2. So 3C2 minus C3 will be equal to 5. And finally, you are going to get, or let me finish with this. So on this plot, C1, C2 will be 0, so I only have C3. Now meanwhile, remember you can divide through here by minus 2, so that the whole of this will turn to 1. You are allowed to divide when it comes to row reduction. Once there is a common factor, you can divide to make your work easier. So if I divide through by minus 2, I am going to get minus 2 over minus 2 is 1, and 4 over minus 2 is minus 2. Okay, so that helps my work. So what it means is that if I now multiply through this, C1 will be 0, C2 will be 0, then this is just going to be C3 is equal to minus 2. Have you seen what that did for us? Even though we would have still gotten the answer if we had written minus 2 C3 equal to 4. By the time you divide, you still get C3 as minus 2. So but what this has done is that it has given you your C3 immediately. Okay, so from there you now do what we call backward substitution. Remember what we did here is Gaussian elimination, and so the first is to get the echelon form, then the second part is to do a backward substitution to now get the remaining values. So we have C3 as this, and so from equation 2 now, if I substitute my C3, I'm going to have 3C2 minus 2. My C3 is minus 2, should be equal to 5, and that's going to give me that 3C2 is equal to 5. Remember, this will become plus 2, and so if it crosses over, it will become minus 2, and that will give me 3, and therefore my C2 is equal to 1. C2 is equal to 1. All right, okay, so that's beautiful. And then on this side we can get our C1 by substituting C2 and C3 here. So we have C1 minus C2, which is 1, plus 2 times C3, which is minus 2, and that's equal to minus 1. Okay, so this is going to be C1. We are going to have, this is minus 4 minus 1, and that's minus 5 is equal to minus 1. Therefore, our C1 is equal to minus 1 plus 5, which is equal to 4. Okay, so our C1 is equal to 4. Okay, so if we go up a little bit again, sorry, pay attention here. I think I made a mistake here. Okay, yeah, this thing is minus 7. Oh my god, remember your equation 1 was not changed at any point, so this was minus 7 here, so it should have remained minus 7. Okay, that's a mistake, sorry about that. Okay, so our equation 1 constant should remain minus 7 and not minus 1. Okay, so this should be minus 7, and so bringing this over here should have given us minus 7 plus 5, which will be equal to minus 2. Okay, sorry about that. All right, okay, therefore you can now write out our C1 as minus 2, C2 as 1, and then C3 as equal to minus 2 as well. So these are the values of C1, C2, and C3. So if you are able to carefully write these 3 transformations of this particular matrix, augmented matrix, down to this place, then from there you can generate this. I think this can enter in one line of your material, that's up down to this place, and then you generate this. From there you now bring out your C1 down to C3. Okay, so and that is that for the question E. Okay, so we move over to question F, if there is. Let me check. Okay, yeah. Okay, so but before we go to question F, remember we were trying to express this as linear combination, so you can finally do that. permit me to increase this at this point. Okay, so that means our so they even said it there. So finally we now present our C1 P1, yeah, blah blah blah, as a linear combination. So down there after that line in between, before you get to F, so you just substitute the values of your C1 C2 into that equation. So you are going to have C1 is -2, so you have -2 P1, then C2 is 1, that means plus P2, and then C3 is -2 also, so you have -2 P3 is finally equal to -9 -7x -15x squared. Okay, and this is the required linear combination. Okay, so and that completes our question E. Okay, so before we go over to F, okay, excuse me. Okay, so continue to give like a thumbs up to the video, the live section of the video. All right, continue to do that. So while we go over to question E, continue to do that. All right. Okay, sorry, to question F. Okay, so straight away to question F. What is he giving, or what are we giving there? Right, so there we are asked to, okay, so it says let for F, so let B1 be equal to 1 0 0 and B2 be equal to -3 4 0, and your B3 is equal to 3 6 3 minus 6 3, and then X, let me see if I can write that X there, and then X as -8 2 3 -8 2 3. Okay, I just wanted all of them to enter that line. And so they said give at least 2 reasons why the set S equal to B1 B2 B3 shall be called basis of R3. Okay, so give at least 2 reasons why you can call the set of B1 B2 B3 a basis. Okay, so remember what we defined basis as, and that's actually why they took time to allow us give those definitions. Okay, so what are those things that we define as for a set to be a basis? One, we said that the set must be linearly independent, and then second, we said that it must span the vector space. So they are asking us to show those 2 things here, meaning we should show that B1 B2 and B3 are linearly independent, and then we should also show that it spans R3. And to show that it spans R3, they gave us an element of R3, so we should just show that this is a linear, so that this X is a linear combination of all of this. That's actually what that question is asking for. Okay, so let's see, all right, what we are to do. Okay, so now we begin. So to show that, to show for linear independence, all right, all we need to show is that if I have, right, if I form vectors from this, okay, and what will be the nature of the vectors, sorry, matrices, I mean, okay, so I'm going to have something of this nature, right? Solution. So the first part is that I want to show that this is linearly independent, okay, so, and to show that, all I need to do is form a matrix from that, okay. So, and if I do, I'm going to have something of this nature, okay. So I'll have 1 minus 3. Now I'm picking the first element, and then 3, and then I have 0, 4, and minus 6, and then I have 0, 0, and then 3. Okay, so when you are able to do this, okay, so you can show that they are linearly independent by showing that this matrix is invertible. Okay, so the question is this matrix invertible? Okay, so how do we show that this matrix is invertible? Is to show that the determinant is not 0. Okay, so remember the question is give at least 2 reasons to show that the set of this b1, b2, and b3 is a basis for R3. Okay, so we show that, you can put it here, we show that b1, b2 are okay, you can say S must be linearly independent. S must be linearly independent. That's the first thing you want to show. And so to show that, we now show that this must be invertible. Must be invertible. Okay, and to show that that is invertible, we now show that the matrix, sorry, that the determinant is not 0. And so assume that this is matrix A. So we want to achieve that A determinant is not 0, and A determinant is 1 into 4 times 3, which is 12, minus 0, okay. Then minus of this is plus 3, is into, here you will have 0 times this, okay, so which is 0, and this times this, of course here is 0, and then finally plus 3, you terminate here, so this will be 0 also. So with this alone, you know that your determinant is not 0, so your determinant is equal to a number, so it's not equal to 0. Therefore this matrix is invertible, and so we can now conclude that the set S is linearly independent. Okay, and then the second condition is that it must span your R3. Okay, and to show that it spans R3 is to show that we can determine some C1, C2, C3 such that a linear combination of that C1, C2, C3 with this B will be equal to this X. So in other words, we are trying to show that, okay, I think this board is filled up, so but let me try to reduce it so that we can probably do what we want to do here. Is it going to enter here? Is it going to enter here? Okay, will it enter here? Okay, let's see. Now what we are trying to show is that if we perform a reduction on this, and this is already reduced, look at it, minus 3, 1, 0, 4, minus 6, and then 0, 0, 0, 3. So this is already reduced. That if you produce some C1, C2, and C3 with this, that it is going to be equal to our minus 8, 3, 2, and 3. Okay, so that's actually what this is saying. Is that correct? Okay. So can we achieve that? Let's see. So this times this, anywhere, if you do a multiplication here now, you are going to get that 3c3 is equal to so let's equate it. Okay, so this will be minus 8 2 3. So remember, we are saying that if we solve this equation that we can actually get values for c that will make this a linear combination that will produce our x. Okay, so let's try to do that. So here now, if you solve this, you're going to get 3c3 will be equal to 3. So which means that c3 alone is equal to 1. So remember, if you use this to multiply, you now get, and here you can cancel by 2, but let's leave it. So you're now going to get 4c2 minus 6c3 is equal to 2 here. Okay, so and you already have your c3, so you put it as 1. So you have 4c2 minus 6 is equal to, I needed green, is equal to 2. So 4c2 is equal to, this coming over here will become 8. And so what it means is that our c2 is equal to 2. Okay, so then we are getting, for c1, the whole of this will multiply here. So you have c1 minus 3c3, c2, sorry, and then plus 3c3 is equal to this constant, which is minus 8. And here you already have your c2 as 2, so this is going to be minus 6. And then if you put c3 as 1, this will be 3, and that's equal to minus 8. If you come up here, so you get that your c1 is equal to minus 8. Of course, this plus 3 is minus 3, and so it will turn to plus 3 here. So our c1 is equal to minus 5. So invariably, you are saying that you have produced 3 scalars that will multiply with b1, b2, b3 to give you x. And so that means you can actually span b1, b2, b3 into any vector from R3. Okay, and that's enough reason. So in other words, here what you will conclude here now is that, let's go to another page. So what you will conclude there, therefore, is that our a times x is actually equal to, is consistent. That means it has a solution. Your a times x is consistent, and so can actually give you minus 8, 2, and 3. Remember that we solved earlier to get the values of this that will multiply with a to give us this. And so what we are now saying is that if we multiply a by this, that is going to produce some, it will definitely produce some values of c. Okay, so that means I can actually say that my x spans, that my s, which is equal to b1, b2, b3, that it spans R3. Okay, so and that is the second condition that completes that it forms a basis for the vector space R3. Okay, so that's what they expected from us there, and that question happens to be Fi. Okay, so this is Fi. So there is another one, II, and so for II we are to show that, let me see the question. Okay, so let's see. For II, we are told to find the coordinates of the vector x relative to basis s. In other words, we should find the coordinate which we usually represent this way, coordinates, is that, yeah, coordinates of x relative to basis s. Wow, I love this. So this thing that we are told to find is actually written this way: coordinate of vector x relative to basis s. So you have s here, and that's what they gave us there. Okay, so to find that, what are you expected to do? To get the coordinates of that is simply, okay, how can you write, let me give you the simple interpretation before we go into the solving. Okay, so what that is saying is, can you express, or let me put it as a row vector, can you express, your x is minus 8, 2 and 3. Can you express this as a linear combination of basis s? So when you are able to get it, the coefficients that you've gotten, which are your c1, c2, c3, you now put it in column vector. If you do that, that is the coordinate vector you are looking for, or the coordinate of x relative to that basis. Okay, so in other words, we want to express this as c1b1 plus c2b2 and then plus c3b3. So we want to get the values of c1, c2 and c3 that is going to give us the value of s, of this x. But let's go back a little bit to our previous page, and that's exactly what we actually achieved here. Okay, isn't it? That's what we achieved here. So we actually got c1, c2, c3 that you will multiply with b1, b2, b3 to give you x. Okay, so if that is what we achieved, then there is no point stressing it again. So we just go back here and tell them that our coordinate vector is actually, you can put since minus 8, 2, 3, which we got above, is equal to, what did we get as c1 above? We got c1 as let me recall. Let's go to the page. We got as minus 5, c2 as 2, and c1 and c3 as 1. Okay, minus 5. So we got minus 5 b1, and then 2 b2, and then c3 as 1. Am I correct? Yeah, c3 as 1. So you have b3, so just 1 will be here. You can leave it there. So that invariably means that if we pick out these coefficients, which is going to give us 5, minus 5, then 2 and 1. So just put this in a column vector. If you do that, you would get, therefore, that your coordinate of x with respect to the basis s is equal to your vector minus 5, 2 and 1, and that is your solution. So you don't necessarily have to solve this again to see whether you will get c1, c2, c3, because we've already done that. But then there is need to run a check. Let's be sure that what we did is actually correct. Okay, and to run that check, just substitute your b1. So here we have 5 into b1, and our b1 is 1, 0, 0. Then plus 2 into b2, and our b2 is minus 3, 4, 0. And then our 1 into b3 was our b3. B3 is 3 minus 6, 3. Okay, all right. So can this give us x? Let's try. So this is going to be minus 5, 0, 0. This one will be minus 6, 8, 0. And then this one is going to be, where is it? This is going to be 3 minus 6, 3. so that we'll be sure of what we have done, and if that is not what we needed, we can try to do something else. And what is it going to be? So let's add. You know, addition of vectors is column component wise. So minus 5 plus minus 6 is minus 11, plus 3 is minus 8, comma 0 plus 8 is 8, then plus minus 6 will give you 2, comma 0 plus 0 plus 3 will give you 3. And that's exactly equal to our x. Am I correct? Yes, that's our x. So you have shown that x is equal to minus 5b1 plus 2b2 plus 1b3. So just pick out those coefficients, use it to form a column vector, and that will give you the coordinate of x with, sorry, did I write coordinate of u? This is the effect of mass 203. Okay, so this is coordinate of x with respect to basis s, and that is the solution. Remember, you don't need to do this check. You actually do not need to do the check, so just stop here. But if you have the time and space in your material to run that check, then that will be okay. Okay, so and that's the solution for question FII. And so we move over to, okay, it has up to 3. So we move over to III, which is the third one under F. And then there they said, given the coordinate vector relative to the basis S, that is coordinate of x relative to s as this, we should find x. Okay, so here we are given that the coordinate of vector x relative to the basis s is equal to minus 3, 1, and 6. Okay, then what is the value of x? Okay, so what x will generate this coordinate vector? Okay, so what do? That means we are going to be doing what we did here in a reverse direction. Okay, so that means we are looking for, okay, so watch it. So we want to make x, our x, which is minus 8, or let me write it, solution. So here we want to make our x to be equal to, here now, remember I told you that the coefficients here will form this coordinate of x. So that means you pick out minus 3 and multiply by the b1 of this set S. Then the next one will multiply the b2, okay, and then the next one will multiply the b3, okay, so which is 6b3. All right, so we are saying what x will this linear combination generate? This particular question is so beautiful. Okay, so let's try that. So you substitute. We have our b1 as 100, and we have our b2 as minus 340, and finally we have our b3 as 3 minus 60, if I am correct. Yes, 3 minus 6, okay, 3 minus 6, 3. Okay, so all we need to do now, first of all, multiply out. This is going to be minus 300. This one remains unchanged. Okay, the coefficient is 1, and this one changes to 18 minus 36, 18. Okay, and then we are now adding the vectors, remember, component wise. Okay, and if we do that, we will have this plus this will be minus 6, minus 6 plus 18 is going to give us 12, if I'm correct. So there we are going to get 12. Okay, so which is comma here. I just saw something that is funny. Oh, okay, don't mind me. So here we have 0 plus 4 is 4, plus minus 36 will give us minus 32. Okay, and then 0 plus 0 plus 18 will give us 18. okay, and therefore that is the value for our x. So our x is equal to that vector there. That's beautiful, very beautiful. Okay, so and that completes the question for just number 1. Okay, so there's a lot of exercises in this material. So and so number 1 took about 3 pages. Okay. Okay, so the next now is to go over to question 2. Okay, so for question 2, we have complete this in terms of linear combination. Okay, so it says the equation ax equal to b has a solution if and only if b is a linear combination of the columns of A. Okay, yeah. So if I have a matrix matrix A, all right, multiplying a vector x, so it is going to have a solution. That means it's going to be consistent. Okay, has a solution if and only if, and we said that earlier in question 1. So it has a solution if and only if b can be expressed. Okay, so if only if and only if b is can be expressed as a linear combination. If b can be expressed as a linear combination of the column vectors, as a linear combination of the column vectors of A. All right, so you know that every matrix can actually generate column and row vectors. So for instance, do I have a matrix here? No. Okay, I can quickly just give an example. If this is a matrix, say 1, 2, and then 3 minus 4, for instance, so you can get 2 row vectors which are 1, 2, and then you can get 2 and then 3, minus 4, and you can get 2 column vectors 1, 3 and then 2 minus 4. Okay, so these are the column vectors of this matrix, while these are the row vectors. Okay, so we are saying that if you have a matrix A and is multiplying a vector x, that ax can only be equal to b, can only have a solution if your A is expressible as a linear combination of your B. Okay, so your B is expressible as a linear combination of the column vectors of A. All right, sorry about that mix up. Okay, so we go over, remember that this is question A, so we go over to B part. Okay, so to the B says provide one reason why the vectors v1 equal to this, one reason why v1 equal to minus 3, 7, and v2 equal to 5, 5, shall be said to form a basis of R2. Okay, one reason why they are a basis shall be a basis, let me just put it that way, a basis for R2. Okay, so and what did we say about basis? We said that number 1, it should be linearly independent. Number 2, it should span your R2 such that any element of R2 can be formed by a linear combination of this. Okay, so what do you do there? So you can quickly try to show that it is linearly independent by showing that the matrix is invertible. Okay, and then Okay. So that's actually what I said here. So the one reason is that, okay, you can actually do it by just a reason. Are we supposed to show that? They just say provide one reason. So just the one reason can be one that v1, v2 are linearly independent. They didn't ask you to show it. They just said one reason, linearly independent. So, and on your own, you should be able to show it. That means for their linear combination to be equal to 0, your v1, your scalars must only be 0. So let me quickly show you what it means to actually do linearly independent. So you're saying that for c1 v1 plus c2 v2 to be equal to 0 0, then my c1 and c2 must also be 0. So in other words, you're saying that c1, which is minus, that's I'm multiplying now, minus 3 plus c1, then plus 7 c1, plus, now I'm multiplying this, 5c2 plus another 5c2, okay, is equal to 0. That means you're saying that if I have okay, okay, so this should be equal to 0 0. So what we are saying is that if my minus, where is my marker, minus 3c1 plus your 5c2 should be equal to 0, and then your 7c1 plus 5c2 again should be equal to 0, then the c1 and c2 that should do this should also be equal to all zeros. Okay, so if we perform a row reduction on this and we get c1 and c2 to be anything outside zeros, then you say that they are linearly dependent. But if we get the two of them as 0, then they are linearly independent. But they didn't ask us to show that here. They only said we should state a reason for this to be a basis. So you can say 1, v1 and v2 are linearly independent. 2, you can say that your where is it, that your v1 and v2 also spans your r2. Okay, should we put it together? Okay, let's see. They are linearly independent and spans r2. Okay, so they span r2, and then you can remove that s because it's a plural. So they are linearly independent and span r2. Okay, so that's what we want to say there. And then the second one, like we did in question 1, you are going to be showing that the matrix formed by this in column approach, that's this, and then this, that it is consistent. And how do you show that it is consistent? That these column vectors are linear, are a linear, where we defined it up there. That means they can form a column linear combinations. Okay, so you can form a linear combination of the columns and it will be equal to any vector in R2. Okay, so that means we are saying that this should be invertible. Okay, so once this happens, we used it in question 1 to show basis. All right, and then okay, so and then you can find other conditions also to use. So, but of course this first one is even enough because that's the definition for basis of a given vector space. All right, and so we move over to C. Okay, so question C says that we should, what is the dimension of the subspace H in R? Okay, let me try to write it. What is the dimension dimension of the subspace H in R2 if that is spanned what's wrong with this marker? Mind yourself. That is spanned by the vectors v1. Okay, so they gave us the vectors v1 equal to 2 and minus 5, v2 equal to minus 4 and 10, and then v3 equal to minus 3 and 6. Okay, so they are asking us to show the dimension of the subspace that is spanned by these three vectors. Okay, so you say that look at this. So from what you are given clearly, it is obvious, and then they even said it here from the hint. Let me write that solution. So from the hint, you can see that your V2 is actually a multiple of V1. Okay, so we can see, all right, that V2 is a multiple of V1. Okay, and then of course you can see if you multiply this by minus 2, you will get this. Okay, so what does that mean? It means that our V1 and V2 are it means that V1 and V2 are linearly dependent, and that's what they're asking us to say there. That's the first space there. This makes us to say that V1, so this implies that V1 and V2 are linearly independent. So that's first space there, just put linearly independent there, dependent. So once a vector is a multiple of another vector, then both of them are linearly dependent. Okay, that's one way to show linear independence, dependency. Okay, and then they now said, on the other hand, V1 and V3 are linearly independent. So that's another statement there which you are to feel. So V1 and V3 are linearly independent. Okay, because you can clearly see that the other one is not a multiple of the other. Okay, so none is a multiple of each other. Okay, it seems that my board is red. Let me finish this and try to charge it. Okay, so I think that's why it's shaking. Okay, okay, so just give me a moment. Where Okay, maybe I should use this here to charge this one. Okay, let's see how far we can go, and then I'll try to charge all of that. Okay, so here, so that is what fills the next space there, where we are told to fill in what is the relationship between V1 and V3. So the relationship is that the two of them are linearly independent. And then the other part now says, okay, I think that's all. Okay, so what is the dimension? So the dimension, therefore, is just going to be 2, because you can clearly see it, that it is only 2 out of the 3 vectors that produce linearly independent vectors. Okay, so we can therefore say, we can therefore conclude that the dimension of your dimension of H is equal to 2. Okay, so is equal to 2. All right, so that's just it, because of all the vectors of H that we have, only 2 of them are linearly independent. Now he says, what is the dimension of the subspace this that is spanned by these vectors? So he's saying that these vectors, all the 3 of them, spans R3. So the implication is that if you can get out of these 3 vectors that spans, so the ones that are linearly independent form, the number of them that are linearly independent forms the dimension of the vector. Okay, or the vector space rather. Okay, so and that is that for that question C. So we go over to the next one, which is D, and there we are told to find the basis and dimension of H. Let me try to write that. Find the basis and dimension of H, which is given as, our H is given as, okay, so here my this thing is beginning to disturb, and that's because it's not charged. So should I end this one here and then we start up another one? Okay, but I'm trying to see if I can complete this particular number. That's number 2. Oh, number 2 is a little bit long also. Okay, so that means we can stop here. Should we? Oh, okay. Okay, let's see. Since it's a bit stable now, let's see if we can finish. Okay, of H in R2, that is spanned by the vectors. Okay, what am I saying? Sorry, I'm rewriting the question in number 2C. Okay, they gave us R2. Sorry, H. Sorry about that. Okay, so they said H is the set of ABC, okay, in R3, such that let me try to see if I can finish writing this here, such that no, I won't. Okay, so let me even come down, such that here you have A plus B, is that plus A minus 3B plus C is equal to 0, comma, b minus 2c is equal to 0, and then I think that's all. Okay, no, and then 2b minus c is equal to 0. Okay, so this is what they gave us. This is so beautiful, a very beautiful example. In fact, they've almost completed what you're supposed to do by giving you this kind of set. Okay, so what does that mean? And they even started by giving us a hint. And what is it? So you just form a matrix from this set. So H is of this form. So you can actually write it out this way. So you have A minus 3B plus C is equal to 0. Then you have B minus 2C is equal to 0. And 2B minus C is equal to 0. So from here you can generate, or even without using matrices. But since they used matrices, let's do that. So we are extracting the coefficients here. We have minus 3, 1, and then on this side we have 0, and then because there's no A, so you have 1 minus 2, and then here you have 0 also, 2 and minus 1, and that is multiplying your ABC to give you 0, 0, 0 on the right hand side. Okay, so right, and so all we need to do is to just reduce this to its echelon form, and when we do that, then all the column vectors, the number of column vectors you have, will actually give you the number of the basis and also the dimension of the vectors. Okay, and that's just it. All right, so what do? Just finish up here. This place has already been reduced, so we just finish up this place, and so this is going to give us, so if I transform this, I'm going to get, what's going to be the transformation? Remember, row 1 and row 2 will remain the same, okay, because you've already done the reduction you wanted there from the question. So here I only want to remove 0 here, and to do that I'm going to, remove 2 to 0. So I'm going to have row 3 minus 2 row 2, because this is going to be my pivot now, and so I'm going to have or let me leave that. Okay, so that's my pivot. So I'm going to have 2 minus 2 times this is going to be 0. That's what I want to achieve. And then here I have minus 1 minus 2 times minus 2. That's going to give me minus 1 plus 4, which is 3. And then, okay, so when I have 3 there, remember I have A, B, C here. And so this is going to be equal to my 0, 0, 0. Okay, so immediately I have reduced this into the echelon form, and so I can conclude. After I reduced it, no row was eliminated. So you have 3 rows there, and then you have 3 columns as well. Okay, so by implication, the 3 rows are going to form the basis that you need, and then that means the 3 of them will now be the dimension. Will be the basis, and then the dimension will be 3. So remember, they said we should find the basis and the dimension. So what that means, that our basis is equal to the set 1 minus 3, 1, comma. So we are picking the row vectors, not the column. So this and then this one, and finally you have 0, 0, 3. Okay, if I'm correct. And so what that now means is that the dimension, your dimension is simply equal to the number of vectors in your vector space, in your basis, and the number of vectors in our basis is 3. I want to be sure that it is the row vectors I'm supposed to pick and not the column vectors. Okay, confirm that, although I will get back to it. So let's see. Okay, either of them actually, either of them should form a basis. Okay, either of them should form a basis. All right, so that gives us the basis for what we are looking for, and then the dimension is equal to 3. Okay, and that's for question D. Am I correct? Is that what we did? Okay, yeah. So that's for question D now. Okay, and then we have question E. Yeah, we have question D. Okay, so but before you go, there's something they wrote here for us to confirm. They said okay, after doing that matrix, they say we should be convinced that we know the reason why we should say that H has no basis. Thus, okay, let's see first. Let's see that and be sure of what we have. Okay, so okay, first of all, okay, yeah, look at this, okay. First of all, let's look at this. Come back here, let me check something here before making this conclusion. Okay, look at this. If we do this multiplication now, we are going to have I think we are going to get all our A, B, C to be equal to 0. So this is going to give us, of course, the first one is going to be A minus 3B plus C equal to 0. The second one will be B minus 2C equal to 0. And then the last one will now be 3C equal to 0, which is going to give us C equal to 0 when you substitute here, B equal to 0, and when you substitute here, A equal to 0. So all of them are linearly independent. So you have produced that the row vectors self are linearly independent, or even the column vectors. So the column vectors. So we have shown that they are linearly independent because we are getting all our A's to be, all our constants for the linear combination to be 0. So I still do not believe that. Okay, so if you permit me, I'm going to now still make that conclusion that the basis is equal to 1 minus 3 1, and then you have 0 1 minus 2, and then 0 0 3. Okay, so where the dimension will be equal to 3. So but I will come back to it. Okay, so because we are told to be convinced that the dimension is 0. Okay, so we'll come back to it. When we do, we will be sure of that. So but take note of that. You can remind me of this later, and then if there is need I can make necessary corrections. Okay, so let's look at E now. So E says find the okay okay, so let me end this here and then try to charge what my writing pad, and then I'll be back in the next section to continue from 2E, and then we now get into 3. 2E is the last question here, so see you in the next section as quickly as possible.